In this video, we are going to be doing example 11.8, the merry-go-round. A horizontal platform in the shape of a circular disc rotates freely in a horizontal plane about a frictionless vertical axle. The platform has a mass m equals 100 kilograms and a radius 2 meters. A student whose mass is m equals 60 kilograms walks slowly from the rim of the disc toward the center. If the angular speed of the system is 2 radians per second when the student is at the edge, what is the angular speed when she reaches a point r equals 0.5 meters from the center? I can tell immediately that this is going to be a conservation of angular momentum problem because the initial angular momentum has to equal the final angular momentum. The initial and the final will be equal because in the beginning, there's a larger moment of inertia with the student out here, and when she moves closer in, the moment of inertia is smaller. So the merry-go-round will speed up. The first thing I'm going to do is find the initial and the final moment of inertia of the system. So the initial moment of inertia of the system is the initial moment of inertia of the person plus the moment of inertia of the merry-go-round. The person we can just treat as a point particle, and remember the moment of inertia of a point particle is their mass times the distance from the axis of rotation squared. So for the person, their mass is 60, her initial distance from the axis of rotation is 2. Then the merry-go-round is a solid disk, and if you recall, the moment of inertia for a solid disk is mr squared over 2, so that's m r squared, and then the 1/2. So the initial moment of inertia of the system is 440. The final moment of inertia of the system, the merry-go-rounds won't change, but the person's will. Again, we can treat the person as a point particle. The only thing that has changed is her distance from the axis of rotation, which is now 0.5. Her mass doesn't change, so it's 60 times 0.5 squared. Then the moment of inertia of the merry-go-round does not change either. The final moment of inertia of the system is 215. Like I said earlier, angular momentum is conserved, so the initial will equal the final. The initial angular momentum is the initial moment of inertia times the initial angular speed, and that'll be equal to the final moment of inertia times the final angular speed. This problem asks us for the final angular speed. So we plug in what we know. 440 for I initial, 2 for omega initial, and then 215 for the final moment of inertia. And then we just solve for the final speed, and we get 4.09 radians per second. The question also asks us to compare the initial kinetic energy to the final kinetic energy. The initial kinetic energy will be 1/2 I omega squared. That's just rotational kinetic energy. So that'll be 1/2 times 440 times 2 squared, which is 880 joules. We want to use the same formula for the final rotational kinetic energy, but this time it'll be 1/2 times 215 times 4.09 squared, and that equals 1,798 joules. So what we can see from this is that the kinetic energy of the system is not conserved because the collision is not elastic. It's kind of like the rotational version of an explosion collision or an inelastic collision. The reason the kinetic energy increases is because the student does work in order to move herself closer to the center. So she is adding kinetic energy to the system because her chemical potential energy has turned into kinetic energy. And that's that problem.